Hello and welcome to Database Management Systems. I'm Jovita Christie, and in this video, I'm going to explain to you how to calculate closure of a set of attributes. So let's begin. Closure of a set of attributes helps us to identify a primary key or a candidate key of a given relation. And let's see how we can calculate it. So if you are given a relation R with attributes A, B, C, G, H, and I, and the functional dependencies A determines B, A determines C, CG determines H, CG determines I, B determines H, and you are told compute all the candidate keys of R, then this is how you will do it. So you will basically calculate the closures of all the attributes given here. So to do that, you need to, first of all, start with single attributes, which means I will start with A and I will compute the closure of A. To calculate the closure of A, you will create a set, and in the set you will add, first of all, A itself. After adding A itself, you will check what else can be added. So the first functional dependency is A determines B, and on the left side there is A, and A is also present in our set. So we can add B also to our set. The next functional dependency is A determines C. The left side contains A, and A is present in our set. So we can add C also to our set. The next functional dependency CG determines H, but we do not have both C and G in our set. We have C, but we don't have G, so we cannot add H. And same is true for the next one, CG determines I. We don't have C and G both, so we cannot add I. The last one is B determines H. Because we have B in our set, we can add H. So this is what A plus looks like, closure of A. But you can see here that I did not get all the attributes of R. There are G and I missing. So we can say that A is not a candidate key. We can call some attribute or a set of attributes candidate keys only when they can generate, the closure can generate all the attributes, but we did not get it. So this is not a candidate. This is not, A is not a candidate key. And next we have B. So with this we have B plus, and we are going to start from here. So because B plus we are calculating, so B itself will be a part of the closure. And then you cannot add anything from the first 5 because on the left hand side it is not B. But I can add this dependency because left hand side is B, so I can add H. Next I'm going to try B plus. B is also not a candidate key. I don't need to say that because it does not have all the attributes. Now let's try C. So this will be C itself. And then if you check all the dependencies, there is not a single dependency that contains only C on the left side. So I cannot add anything else to this. And this is not a functional this is not a candidate key. Now let's calculate, there is no D, there is G. So let's calculate G plus, which means I can add G itself. But then once again, there is no functional dependency that contains only G on the left side. So I cannot add anything else, and that is it. So this is not a candidate key either. Next I have H. So I can add H itself, but after that, once again, there is no functional dependency that has H alone on the left side. So this is not a candidate key. And next we have I. So I can add I itself, but there is no functional dependency containing only I. So that's it for the closure. So that's why I is also not a candidate key. When you have exhausted all possibilities with single attributes, you will try with two attributes. So now we will take combinations of attributes. And so we are going to take AB plus. When you take AB plus, you get to add A and B just as they are. After that, you will check the functional dependencies. Using the first dependency, I can add B, but B is already there. Using the second dependency, I can add C. Third dependency, I cannot because I don't have G. Same is true for fourth. For the fifth one, I can add H because I have B. But once again, I did not get all the attributes, so this is not a candidate key. Next thing I have is AC plus. So I can have A and C. And after A and C, using the first dependency, I can add B. And using the last dependency, I can add H, and that's all. But I didn't get all the attributes. So this is not a candidate key either. Next, I'm going to compute AG plus. Okay, let's do AH plus. It doesn't matter. So I have added A, I have added H. Because of A, I can add B, I can add C, and that's all. This is not a candidate key. Next, I have a G plus, which is remaining. So AG plus. In this case, I'm going to add A and G. And now for A, because of A, I can add B, I can add C. Now, notice that I have C and G both present, which means I can finally make use of these two dependencies and go ahead and add H and I. And I can add H because of B determines H, but H is present. And you can see all the attributes are there. There is A, B, C, G, H, and I. So that means AG plus this, what we calculated, AG, is actually a candidate key. The combination of A and G forms a candidate key. But that's not where your calculation ends. Your question was to compute all candidate keys, not just one. So until you have found all the candidate keys, or you have decided that there are no more candidate keys, till then you have to continue calculating. So we are going to proceed with AI plus. AI plus would be A and I. What else can I add to it? I can add B, I can add C, and because of B, I can add H, but there is G missing. So AI plus is not a candidate key. Now we are going to try combinations with B, and because we've already combined A and B before, we don't need to do BA plus, but we haven't combined B and C, so we are going to combine B with C. So we are going to do BC plus, and BC plus is equal to B and C. And after that, if I check, I can add H, but I cannot add anything else. So this is not a candidate key. BG plus would be equal to B and G. Because of B, I can add H, and that's about it. So this is not a candidate key. Then I have BH plus. So I can add B, I can add H, but after that, there is nothing to add after that. So this is not a candidate key. And finally, I have BI plus. So I can add B, I can add I. Because of B, I can add H. And that's about it. Not a candidate key. Now let's try with C. So we are going to try CG plus. CG plus means I can add C, I can add G. Now because of C and G, I can add H and I, but I cannot add A and B. So this is not a candidate key. Next, I can have CH plus. So C and H will be present, but because of those two, I cannot add anything else. So this is not a candidate key. And CI plus, this means I have C, I have I, but I cannot add anything else other than this. So this is not a candidate key. And that's it for C. Then we can check G. GH plus is equal to G and H. Nothing else can be added, not a candidate key. GI plus is equal to G and I, but nothing else, not a candidate key. And finally, HI plus, which is equal to H and I, but nothing else. This is not a candidate key either. So to conclude, as a conclusion, I can write that AG is the only candidate key. AG is the only candidate key present for this table. So if you had to choose a primary key, all you could choose was AG, combination of AG. Now you might wonder that I did combinations of 2, but what about combinations of 3? We wouldn't be doing that because a candidate key essentially is a minimal super key, which means there are no extra attributes in it. If I combine any attribute with A and G, it will definitely form a key. But will it be a candidate key? It won't be, because those will be extra attributes when I can already form a key using A and G. So we wouldn't be looking further. However, if there is this type of a question and you get lucky and are able to calculate your candidate key from just single attributes, then you can say that those single attributes themselves form a candidate key without having to worry about double attributes. So one attribute, if you are able to find a candidate key from there, then you don't need to check a combination of 2. So that's how you need to calculate, and that's how you can find out candidate keys and closure for a set of attributes. And that's it for this video. I'll see you in the next one. Thank you for watching.